We have been talking about addition of carbon-based nucleophiles to ketones, aldehydes, carboxylic acid derivatives. The one thing I wanted to just review from last time is this difference when you have an alpha-beta unsaturated carbonyl compound. That means there's a double bond between the alpha and the beta carbons. Organolithiums and Grignards will attack at carbon 2, that is the carbonyl carbon. And you'll get the familiar tetrahedral intermediate, which if this group is a ketone, you're sort of stuck at until you do the aqueous workup. You protonate and you get the alcohol, where the organolithium reagent is attached to the carbonyl carbon. On the other hand, if you use a cuprate, the cuprate will attack the beta carbon. As to why that attack can occur, there's two ways of thinking about it. One is that in a conjugated system, the LUMO will extend over the whole conjugated system, and part of it will be on the beta carbon. If that's a little bit confusing and unfamiliar to you, you can just remember that for alpha-beta unsaturated carbonyl compounds, you can draw a resonance structure that would put a positive formal charge on the beta carbon, and that gives you a clue that the beta carbon is going to be electrophilic. So the cuprate will attack at the beta carbon. One thing I'm not sure if I mentioned last time, that this is the intermediate you get. You make a new stereocenter here, and of course, this carbon is sp2 hybridized before, it's flat, it's the same above or below, so if you make a stereocenter, you got to get both varieties here. Notice that the new bond you form is between the beta carbon and then the first carbon of your cuprate. At this stage, what actually happens is that it's very fast to protonate on the oxygen. In fact, faster to do that than any of the other possibilities. So your immediate product after the addition is this enol. Okay. Did you learn about tautomerization last semester a little bit? Okay. So you know that carbon-carbon double bonds are not as stable as carbon-oxygen double bonds. So you're comfortable, hopefully, with the idea of this equilibrium, where tautomerizing means to change the position of a double bond and the position of a hydrogen. Here in the enol, the double bonds between carbons. Here it's between carbon and oxygen. Here the hydrogen is bonded to oxygen. Here the hydrogen's bonded to the alpha carbon. So once you form the enol, you get tautomerization to the more stable ketone form. Your mechanism takes you through the enol and then says it tautomerizes. The reason your mechanism does this is because that's what actually happens, but the other thing is that it helps you see why addition to the beta carbon is sometimes called 1,4 addition. Because if you think of what we added relative to the starting material, we added this group here and we added the hydrogen. That's the 1 and the 4. Okay? Sometimes instead of calling this 1,4 addition, people will call it conjugate addition. And we'll see some more examples of that a little bit later on. All right, so when you see a ketone and something's bonded to the beta carbon, you might need to be thinking, okay, I could have made that by addition of a cuprate to an alpha-beta unsaturated ketone. All right, questions about that? Okay. Well, the last thing we need to do in Chapter 20 is to talk about what happens when you want to do this kind of reaction in the presence of functional groups that might interfere. So, as an example, let's just draw this ketone, but we're going to put an alcohol here. And let's suppose that we want as our product the diol with, let's say, a phenyl group here. All right, well, if you're thinking in terms of what the reagent must have been, I see that we've created a new carbon-carbon bond at what used to be a carbonyl carbon. So I'm thinking, let's go ahead and use phenyllithium. By that I mean just the benzene ring attached to lithium. And then in a second step, we'll use water to protonate the tetrahedral intermediate. And it sounds good unless you're paying attention, because what you've got in this ketone is an interfering group. What will happen in general, if you have a molecule that's both a strong base and a strong nucleophile, removing protons is really fast, in many cases faster than attacking carbons. And so what will happen, instead of the desired reaction where the phenyllithium group would attack the carbonyl carbon, instead what happens is we deprotonate, and we end up with the conjugate base of our molecule and benzene. So what we have just done is found a really expensive way of making benzene, and we've got the conjugate base of our molecule, which when we add water is going to go right back to our starting molecule. So this is an exercise in futility. It's pointless, and it's a problem. And it is a problem in synthetic organic chemistry, because we're going to want to make pretty complicated molecules that have diverse functional groups, and so we got to have a way of dealing with that. So today we're going to introduce the concept of protecting groups. The idea behind a protecting group is, if you see a functional group that's going to interfere with your reaction, like this alcohol, for example. I don't know if any of you growing up saw Mr. Yuck. It's a sticker you would put on dangerous things to remind children not to eat them. Anyway, I don't know how we're going to communicate that this is a problem and it's going to destroy your reaction. This is what you should be thinking of. Drips of blood. Okay, whatever. That's gonna, I'm easily distracted, I'm sorry. That's gonna that's gonna damage our reagent. So ideally we want to use a group that will mask the problematic features of that alcohol. So the standards for our protecting group is it needs to be easy to put on, the functional group that we want to protect. And that needs to happen in a high yielding way. It needs to be inert to whatever reaction we want to do. In this case, it needs to survive and be unperturbed by the Grignard or the organolithium reagent. And then it needs to be easy to come off. Okay? It needs to be easy to remove in a high yield reaction. If it's not high yielding to put on and then to come off, we are in trouble, because we're going to take a major hit in yield. And when you want to do a multi-step synthesis, you simply cannot afford that. So there are many protecting groups that are available in organic chemistry. There's whole books full of them. We will introduce just a few this semester. You'll be used to the idea. And for alcohols, a major protecting group of choice is going to be the silyl ether. What on earth? Okay, well, ethers, you know, are where an oxygen is bonded to two carbons. A silyl ether will be where an oxygen is bonded to a carbon and a silicon instead of two carbons. Silicon's in the same column of the periodic table as carbon. It has different chemistry, but sort of analogous chemistry. So let me show you what I mean by a silyl ether. Here's how you do the protection reaction. I think we just got another carbon there. Yeah. So we'll use a reagent that is maybe somewhat painful to draw, but is easy to abbreviate. The reagent is this. You have silicon, you have a tert butyl group, you have two methyl groups, and then you have a leaving group. This is tert butyl dimethyl silyl chloride, or, because we like abbreviations, TBDMSCl. Right? What does this reagent do? Well, if this were a tertiary alkyl halide where this atom were carbon, you would propose perhaps that the chloride leaves to give you a carbocation and then a nucleophile can attack. We're not going to draw the mechanism for this, but that's probably what happens here. Probably chloro leaves, leaving a positive charge on the silicon, and then oxygen attacks the silicon. In any case, we're making a new silicon-oxygen bond. And those are pretty stable, as evidenced by the fact that there is a lot of sand on Earth, and sand is full of silicon-oxygen bonds. We need a base to do this, but we don't want the base to be able to interfere with the carbonyl compound. We need the base to soak up this proton on the oxygen, and the base that we're going to use is called imidazole, and its structure is this. We use this again because it's a base that's not a good nucleophile. I don't care that you memorize the structure of imidazole. The basic the basic site is this nitrogen here. You add those two things together and expose your alcohol to that, and you make this molecule. And again, because we get tired of drawing out stuff that isn't going to stay in the molecule to long term, we often abbreviate these protecting groups like this, TBDMS. Whoa. All right, there are lots of silyl protecting groups. This is the one your book introduces. You may encounter others in your future if you were to do some organic chemistry. But the idea is that this group has no acidic proton on the alcohol. So now with our TBDMS group intact, we can do whatever chemistry we want to with the ketone. Now we can do the phenyllithium, followed by a quench with water, and that will give us the desired tertiary alcohol without that other primary alcohol interfering. Okay, so this is the protection reaction where we put the TBDMS group on. Okay, and this is the silyl ether functional group. After that reaction, we need a deprotection reaction. And again, we're not going to worry about the mechanism of this reaction. It's actually very simple. It happens fast and in high yield. The reagent you use is fluoride, F-, but then you need, that sounds like a really bad grade, right? F-. That's too close to home, isn't it? We don't want to, 1, 2, 3, 4. And then because this occurs in organic solvent, we need some counterion that will help the fluoride be soluble. This is called tetrabutyl ammonium is the counter ion, and then this is fluoride, except I can't spell, fluoride, and of course we've got an abbreviation for this as well, TBAF. But it turns out that silicon fluorine bonds are stronger than silicon oxygen bonds. So it's thermodynamically favorable for the silicon group to come off and liberate the alcohol, and probably your byproduct that you can remove, low battery, okay, thanks, probably the silicon group that you are able to get rid of has a new bond with fluorine. This is a byproduct. You don't necessarily need to worry about this. This is the deprotection reaction where we remove the group. Okay? So this is our side step to prevent problems. Yeah?
Is that in the presence of water?
Where's the hydrogen coming from? Is that in the presence of water? Yes, probably. Or if not, there's an aqueous workup step afterwards. I'm not totally sure because actually, though I've done a lot of chemistry, I've never used a silyl ether. So what are you going to do? Yes. So you can assume that we get the proton either from water, either during the reaction or during the workup step. Okay? Other questions? So your task is going to be to determine when a reagent you're using might interfere or be interfered with by an alcohol group, and then to deploy this protecting group strategy to prevent that. Protect, do the reaction that you want to do, then deprotect, and then you can move on. All right. Yes?
So we only use these two specific reagents when functional group is an alcohol?
Well, we only use these two specific reagents when we're trying to protect an alcohol. Yes, for all intents and purposes. Yeah, this is our protecting group for alcohols. There are other things we could use, and there are other problematic functional groups that we'll encounter later. Amino groups we don't typically protect with the silyl group. We'll use something else, but the principle is the same. High yielding protection reaction, inertness to whatever other reaction you want to do, and then a high yielding deprotection reaction. And then you can see how this could get clunky, right? If you're trying to do a synthesis and you have a lot of protection and deprotection steps, that can be problematic. So the really exciting chemistry that gets published in Nature or Science is often about cool reactions that you can do without protecting groups. And that's when people go, ooh, because everybody knows that you usually have to use this protecting group strategy, and it's challenging. Okay, others, yeah?
So this you only need to protect when you're attacking with nucleophile that's also a strong base. And so the lithium one is one of them, and then the one with magnesium also has like the same properties.
That's right. Yeah, so the lithium reagent, the Grignard reagent with magnesium bromide, and then the cuprate as well. Those are all going to be strong bases. So if you have an alcohol, yeah, you're going to need to use a protecting group.
Okay.
Yep. Okay. Anything else? All right. So that's it on chapter 20. What we're going to do now is continue on with ketones and aldehydes, but our theme is going to be nucleophiles that are not as strong as the organometallic reagents. Okay? The simplest example of this is what happens if I want to add water to an aldehyde. Well, why would I want to do that in the first place? Not sure, but this is a simple way to demonstrate a principle. It turns out that in the presence of water, there's some equilibration between the aldehyde and the product that you get from addition of water to the aldehyde. This is called the hydrate, and whereas the hydrate suggests that you've added water, here's an oxygen from water, and then the other hydrogen would have been from water. Okay, so mechanistically, what is going on here? Well, if you recall back to the beginning of the semester, which seems like more than just a week ago. Wow. We talked about how it's probably not reasonable for a neutral oxygen to go in and attack the carbonyl carbon directly, because that would have us get a negatively charged oxygen from something that was neutral to begin with, right? And so it turns out that hydrate formation requires us to do this reaction in the presence of a little bit of acid. Now, thankfully, even at pH 7, there's enough acid to make this happen. But mechanistically, what likely occurs is that first you have some amount of hydronium, even a very small amount. You remove the proton from hydronium to get the protonated carbonyl compound. Compounds with positively charged oxygens are often called oxonium ions. This molecule is now more reactive than a typical carbonyl compound. The reason that's the case, you can see because we've got the positive charge on the oxygen, the resonance structure where we put the positive charge on carbon is even more favorable, right? Which means that the carbonyl carbon is even more electrophilic. Now it's okay for water to attack the carbonyl carbon, to attack the pi star at the carbonyl carbon, thereby breaking the carbon-oxygen pi bond. The proton transfer step is an equilibrium step. Water attacking is also an equilibrium step. You can tell that what we've just done is reasonable because we go from one positively charged oxonium ion to another positively charged oxonium ion. This is the familiar tetrahedral intermediate. So all we've done so far that's been different is that we're using a nucleophile that requires acid catalysis, requires us to protonate the carbonyl first, and then the nucleophile attacks. We get to the tetrahedral intermediate, and what we usually do there is we ask, well, do I have any good leaving groups? And that is relative to the OH group that we've got left. If this were negatively charged, it would be relative to a negatively charged oxygen. It turns out this OH group is a strong enough nucleophile to kick off the water leaving group, and that happens, and that's just the backwards reaction. On the other hand, if we use water now as a base to remove this proton, we get to the hydrate form, and notice that we've regenerated in that last step our hydronium. One of the challenging things I've seen students struggle with this mechanism is just the idea that each step that goes forward could also go backwards. This is an equilibrium reaction. And students have struggled with, well, how do I know which way it's going to go? And the answer is, at equilibrium, the concentrations of starting materials and products don't change. So the reaction's actually going nowhere. What you need to be able to do is to push arrows forwards and backwards to be able to rationalize your way through this. Okay, questions so far about this mechanism? Really? Okay, yes.
Does this favor the products of the reaction?
Does this favor the products or the starting materials? It will depend on the aldehyde. I should have actually come with equilibrium constants to give you an example. So I'm sorry I don't have that number. I would guess, depending on the aldehyde, it's a few percent to several percent. That's really hedging, isn't it? But certainly not mostly the hydrate. Okay, was another question?
I would just add, so if it kicked off the water instead of taking off the
That's right. If from the tetrahedral intermediate we kicked off the water, that would just be going back here. So it's an interesting exercise actually to take this in your notes, start with the hydrate and see if you could go backwards. So this isn't a reaction you would actually do. This is just telling you what happens if you put an aldehyde in water or you put a ketone in water. Now your text will show you that you can use the percent hydrate formation to assess how reactive the aldehyde is. Aldehydes are more reactive than ketones. You can form the ketone hydrate as well, but ketones are less electrophilic than aldehydes, so you would expect the equilibrium constant to not be as favorable for the ketone as it is for the aldehyde. And there may be some practice problems that ask you to reason your way through that. All right, so that's kind of a boring example, but this gets you used to the idea of something that you're not used to thinking of as a strong nucleophile, because it's not. Water, using a weaker nucleophile, using acid catalysis to allow it to add to the carbonyl compound. Okay, the next thing we're going to do is do the same reaction but with an alcohol as our nucleophile. Okay, so let's just use those same principles. Let's use a boring ketone just because they're easy to draw, but it doesn't need to just be acetone, could be any number of ketones. Let's use methanol as our nucleophile, and let's say we're using a catalytic amount of acid. The acid of choice that's organic soluble is often, and you may, I think, have been introduced to this acid in 351, often it's para-toluene sulfonic acid, which people write TSOH, some put a P in front of it, but this is an organic soluble, basically sulfuric acid. So let's just, without knowing in advance what the products are, let's see if we can sort of predict what's going to happen. All right, first step is probably, well, what happens when you have acid in a carbonyl compound? The highest occupied molecular orbital of the carbonyl compound is lone pairs on the oxygen. Here is, we'll just use HA for our acid. So probably the first step is proton transfer to give us the oxonium ion. I'm using a forward and reverse arrow there just to indicate that we can go backwards, because it would be straightforward and easy for the conjugate base of our acid to remove the proton from the oxonium ion. The oxonium ion is now more electrophilic than the starting ketone was, and that allows our nucleophile, which is methanol, neutral oxygen, not normally a good nucleophile, but it's good enough now to attack the carbonyl carbon because the carbonyl oxygen is positively charged. That gets us from the oxonium ion to this tetrahedral intermediate with a positive charge on the oxygen from methanol. Now, what happens next? Well, when we have a tetrahedral intermediate, we ask the question, is there a good leaving group relative to what used to be the carbonyl oxygen? And the answer is, well, sure, we could kick off this leaving group as neutral methanol. That would simply be going back to the oxonium ion. And that's a reasonable step. And we will talk about how to control whether we favor the forward direction versus the reverse direction. But for now, let's think about what else could happen. So we could use the conjugate base of our acid to remove the proton from what used to be methanol. And if we did that, that would stop it from being a good leaving group. And that would regenerate our acid. And this, what we're showing you here, this neutral sort of intermediate, has a name which we will come back to. But in general, the reaction's not done here because the acid can now add a proton to the OH group. Oops. That would convert the OH group into a good leaving group. Slide it over just a little. So what would happen if we did that? Well, we would turn the OH group into an OH2 group, which is now a good enough leaving group for a neutral oxygen to kick off. And that generates a new oxonium ion. The difference between the two oxonium ions is before what was attached to the oxygen was a hydrogen. Now it's a methyl group. Go ahead, sorry.
So back to that step where the O is attacking the acid.
Yeah.
Why is it the alcohol O and not the methanol O?
Why is it the alcohol O and not the methanol O? That is a great question. And the answer is, in the previous step, we had the hydrogen on the methanol oxygen. It's very reasonable for the acid to put the proton right back on that methanol oxygen. That would just take us backwards to the previous intermediate. So that's reasonable. That's just the backward step. What we're trying to do is show you what a potential product is, and then we're going to describe how to control whether we go one way versus the other. For right now, it will be enough to recognize that both things can happen. Yeah?
On step 3, should that be like a CH3 instead of a hydrogen?
Step 3. I'm sorry, where am I looking?
Yeah, like right in the
Oh, yes, yes. This reaction does not magically turn a methyl group into a hydrogen. Suddenly I was back with the aldehyde, for which I apologize. Thanks for keeping me honest. What else? Yeah.
So on the bottom left molecule, it's got the carbonyl with the oxonium ion.
Yeah.
There's that other resonance structure that places the positive charge on the carbon. Is that the resonance structure that it will actually attack, or just?
So we've got the question is we've got this resonance structure where the positive charge is on the carbon. Which one is the one that's actually attacked? They're both incomplete descriptions of the same thing, but either is acceptable. Yeah. They both describe the same reactivity. You make a new bond with the carbonyl carbon and the pi bond is gone. Okay, what else? Oh, yes, thank you.
And that's just like the basic idea of resonance structures, right? They don't actually exist, it's just how we look at them.
Well, the idea is that both of these are incomplete resonance structures. They are both incomplete descriptions of the overall reactivity of the molecule. Another way we would say this, if you were thinking in terms of molecular orbitals, that the LUMO, the pi star, is even more polarized towards the carbonyl carbon once we protonate the carbonyl, which makes it more reactive. Yeah?
The oxonium in this and the previous reaction, or at least how it's been labeled, they appear different. Is it just because that's the step, like, is it just referring to the step that it is produced by, or?
So are you thinking about the difference between this oxonium ion and this one? Yeah. Oxonium describes a positive formal charge on an oxygen. You can have that for different reasons. In this case, over here to the left, it's positively charged because of a proton. Here, it's positively charged because of a methyl group. Yeah. So, yeah, oxonium doesn't refer to a specific molecule, but rather the pattern of a positive charge on a formal charge on an oxygen. All right. Good? Okay, so we've got this new oxonium ion, which is, we would predict, based on what we saw before with the previous oxonium ion, that it's going to be reactive at the carbonyl carbon. We're in methanol, and we're using methanol as a solvent, so we have a large excess of methanol. A second equivalent of methanol can come in and attack as a nucleophile. That will give us a new tetrahedral intermediate. With a positive formal charge on what used to be the methanol oxygen. Now at this stage, of course, you might imagine the neutral oxygen kicking down and kicking the methanol back off. That would just take us to the previous step. But, oops, I don't like what the erasing's doing. But instead, if at this stage we bring in our conjugate, the conjugate base of our catalytic acid, we can regenerate the acid to make the final product, which is here. Okay? So this is our final product. All right. That type of functional group where you have two ethers attached to the same carbon, that's called an acetal. That word is acetal. All right. Yes?
So all those steps are reversible?
All of those steps were reversible, yes. Now let's look at that actually and think about strategies we might use to favor one direction or the other. What do you notice? Well, any ideas? Any ideas for favoring one versus the other? Yeah.
Could you distill the final product?
Can you distill the final product? Okay. I don't actually know. I think probably, though you may not have to go to that. So what do we mean by distill the final product? Sometimes if you do a reaction under sort of boiling or refluxing conditions, if your final product has a lower boiling point than anything else in the reaction mixture, you can capture that final product in what's called a distillation column. You basically make it condense on something cold and then drip into a separate vessel. Okay, so that's one strategy. Anything else? Go ahead.
Could you add like a weak base or weak acid to react with your acid or basic?
Okay, so could you add something to react with the acid or base? You're thinking along the right lines, though you probably don't want to do anything to your acid because that's a catalyst. It's neither it's not consumed. Well, it is consumed and then regenerated. So anything you might do to the acid is going to slow down the reaction. Yeah. You change the concentration of the acid, sure, and that would make the reaction faster, probably, if you increase the catalyst. Go ahead. Change the concentration of the alcohol, good, right? If we're adding the alcohol to the carbonyl compound, then using an excess of the alcohol would favor the products. And in this case, usually we're using the alcohol as solvent, so that's going to help us. There's one other thing, and it's subtle because I didn't draw it as a product, but notice that in this step, we lose water. Oh, right. look at what's absent in the product, that carbonyl oxygen. We lose water. So if you have some way of removing water, then you can favor forming the acetal. There are a lot of ways you can remove water. One of the ways you'll use, I think, in 353, if you take that lab, is you're going to use a salt that's hygroscopic. That means it likes to absorb water, and that will pull it out of the equilibrium, and that's going to allow the forward reaction to dominate. All right. So that's kind of a mess, but overall, when you see a carbonyl compound, say in this case an aldehyde, and an alcohol, and a catalytic acid like para-toluene sulfonic acid, the product that you should draw is the acetal. And even if we don't say in this reaction, oh, by the way, we're removing water and using a large excess of alcohol, that's okay. We're assuming that you're doing that to give you the acetal. Okay. Couple other things about this reaction. Well, yeah.
So this works for aldehydes and ketones?
Yes, works for aldehydes and ketones. Yeah. Does it work equally well, or does an aldehyde get a higher yield? I think it's about the same. In any case, we can push the yield to we can push the reaction to completion by making sure it's not in equilibrium. All right. Now, what if you wanted to make the acetal go back to the carbonyl compound? Still going to need acid. Acid's the catalyst, right? So the catalyst doesn't affect the equilibrium. It just makes it faster. So what are you going to do if you want it to go from acetal back to the carbonyl compound? Add water. Use water as your solvent. Use an excess of water. So this, if you see, on the other hand, an acetal, and you see water and H3O plus, then you're going to draw the aldehyde and perhaps the alcohol as the byproduct. And that's just going backwards from here all the way there through the same mechanistic steps. Shall we? Yes, go ahead.
So, sorry, do you want us to memorize like just the products of this reaction, or do you want us to be able to draw the mechanism?
Yeah, the question is, do I want you to just know products and reagents and starting materials, or do I want you to know the mechanism? Yes, I want you to know the mechanism. When I do that, that indicates that this may be an evil thing that I may try to test you on an exam. Okay? Yeah, you should know the mechanism. Let's see. Shall we show you how to get from the acetal back to the carbonyl compound? It'd be practice. Actually, maybe we should do it. If it's boring to you, then great. Hopefully that's not because you're just bored in general, but rather that you already understand it. But if not, it'll be a useful review. So what do we do if we have the acetal and instead we want to make we want to release the carbonyl compound and go back to the starting materials? I'm going to draw an interesting kind of acetal here. In this acetal, both of the alcohols are attached to the same molecule. That would be, and you'll see what the product is going to be when we use water and hydronium. incidentally, if you think that looks like maybe some person with eyes, you're not alone. There's a whole research group at Rice University in Houston, Texas, that has made a career out of making anthropomorphized molecules called the nanoputations, where they use different alcohols to create the image of different kinds of hats on this person. So I just seriously Google it and look at the Wikipedia page. It's whimsical and somewhat ridiculous that somebody's paying for you to make molecules that look like people, but it's kind of fun. Anyway, all right. Look at the mechanism above. The last step for acetal formation was removing a proton from one of the alcohol groups. So in going backwards, the first step should be protonating one of those alcohol groups to turn it into a good leaving group. All right, so let's draw what that would look like afterwards. All right, it's sort of kind of gruesome, and now looks like something sticking out of the poor guy's eye, which is weird. Okay, what was the previous step in acetal formation? In that previous step, we had an alcohol attack a positively charged oxonium ion to give us this product. So, to go backwards, we should have electrons on the neutral oxygen kick down and kick off the positively charged oxygen as a leaving group. And that's going to give us an oxonium ion, where this is the alcohol that left, and it just happens to be bonded to the other oxygen. Okay, see what we're doing so far? Ultimately, we want to liberate this whole group, so what do you think the nucleophile is that's going to do the attacking? You're muttering it, but mutter it more loudly. Water? Okay, if it were the alcohol, that would take us back to here, or perhaps another alcohol, but we have an excess of water. So yeah, we're going to use water as the nucleophile. And I will draw the product there, and that will be all that we have time for today. It will be helpful for you if you can try to complete this mechanism all the way back to the final products, which I'll show you here, the aldehyde and the alcohol. Okay, so we'll pause there, and I will see you Wednesday.